Okay. I'll give everybody a sec to scan the code, and then we will get started. Back and have it. It always does that. It'll just sort of stop presenting for a second. All right, as we're getting fired up, I'm curious, how did this combined homework assignment go? Did it go well? Okay, all right. Assigned on Friday. That's a typo. Hold on for 1 second. That's assigned today. Sorry about that. Okay. So attendance grades are up to date. I want to make sure that, again, everybody remembers we are not going to have class on Friday. As I mentioned, I'm just going to count everybody present for that lecture since it's going to be pre-recorded. What we're going to do today, and what I've done in that pre-recorded lecture, is discuss rigid body equilibrium in 3D. Okay. Now, what you will find is that rigid body equilibrium in 3D is no more conceptually difficult than equilibrium in 2D. It's just longer. I would also argue that we're at the point in the class where these are about the longest problems we will deal with from here on out. In other words, past this, the problems get a lot shorter, they get much more manageable, and are a lot, I don't want to say a lot more practical, but they're a lot more practical to do, I guess I would say. I understand that rigid body equilibrium problems can be long. That's why I'm giving you an assignment today that only has one problem on it, but it's due Monday. I just want to give you time to do it. It's not hard, but there's a lot of steps. I would say that if you understand this problem and understand this, you probably are good with everything in this class, because everything from here on out is much simpler and much more straightforward. I'm not saying this isn't simple. It's just long. So I want to get right into it because I want to make sure that we have time to do this example and do it well. Did everybody get the code? Okay, I'll take that as yes. All right. So we're talking about reactions in 3D. That's what we're talking about, okay? So, if you recall, in 2 dimensions, we had 3 equations of equilibrium. Well, technically, in the land of 3 dimensions, we have 6 equations of equilibrium. 3 forces and 3 moments, okay? Now, I had shown you the boundary conditions in 2 dimensions, and if you remember, if you open your textbook, there's oodles of these things, but really we only concern ourselves with a few of them. Pins, rollers, fixed supports, those tend to address over 90% of the engineering modeling problems that we deal with really on a day-to-day basis. The same thing can be said about 3 dimensions. If you open your textbook, there's tons of these things. There are tons of them, okay? What I am most interested in your ability to assess is, number 1, a fixed support, which is, again, very analogous to a fixed support in 2D. It just is a support condition that can withstand forces and moments in all directions. What the textbook calls a ball and socket boundary condition, which is really just a pinned boundary condition in 3D. So that's a boundary condition that has unknown forces, but not moments. And then maybe something either like a cable or a ball support that only has a reaction in one direction. I'm not worried about all these hinges and pins and brackets where some of them have unknowns and the others don't, because I don't think they make the problems any more conceptually challenging. They just become bookkeeping issues. And I'm all about you learning the concepts. And so that's point 1. Point 2 is these will address, again, the vast majority of what we're dealing with in the real world as engineers. So if you can handle those, we're good. And the best way of making sure that we're comfortable with these is to do an example, okay? So I have here a rigid body 3D equilibrium problem. We're going to spend the entirety of lecture on this problem, okay? So let me pull up the notebook because, like I said, I think this lecture really sort of brings like everything that we've been talking about together in one fell swoop. Okay, so I have a sign that is 5 foot by 8 foot. So it's obviously not a particle. It's a rigid body. The sign weighs 270 pounds, and it is supported by 2 cables and this pin support here at A. Okay, or what the problem's calling a ball and socket joint, essentially just a pinned boundary condition. I want to determine the reaction at A, and I want to determine the tension in each of those cables. That is the goal of this problem. So I'll give everybody a sec to start jotting this down, and then we're going to dive right into it. And just so you're aware, I got kind of wise with this problem because if you scroll down, I copied the image of the schematic again, so I wouldn't have to keep scrolling up and down. I brought my Casio FX115 ES Plus as well in case I got to be put to work. Okay, so I want to try and do my best to draw parallels to what we've done already, okay? And so what we have here is a free body diagram, or we're going to take this and expand it into a free body diagram. And what I mean by that is I want to start off by identifying all of the forces that are on this system, okay? So let's start off with that. So strings got caught. There we go. Let's start off with forces, okay? So first off, if I look at the problem, I need to determine the tension in each cable. So I propose that there is a tensile force right here, and there is a tensile force right there, right? And I think it makes sense the direction I've applied these things. I mean, if here's the sign, I just let the sign go. The sign wants to fall down. The cables are holding the sign up, right? So we're going to have a tensile force here. We'll call this TBD. We'll call this tensile force right here EC. EC. Now there's 2 other forces that we need to consider. The first is the weight of the sign. Now, I'm going to throw a little concept at you. The first is, okay, so let's talk about the 270 pounds. What direction is that 270 pounds going to act? Is it along the X, the Y, or the Z axis? The Y. It's acting downwards, okay? So it's acting downwards, but where do I place that vector, that force vector? Well, what I'm going to do is I'm going to take that vector and I'm going to place it right here, okay? I'm going to place it in the middle of that sign. So basically what I'm saying is that I have 270 pounds acting downwards, but I'm placing it in the middle. I'm using that term middle very loosely, okay? A more descriptive statement would be that I am placing that 270-pound vector at the centroid of this rectangle, okay? Now, we haven't talked about centroids yet. That's going to be after the second exam. But suffice it to say that centroids are, quote-unquote, the middle of a given shape. And so, for now, because we haven't talked about centroids, we're just going to deal with extremely simple shapes, and the middle of a rectangle is going to be right there. I'm going to place it right there. But maybe the question we're going to ask during the after the second exam is, what if this sign wasn't a rectangle? What if it was a triangular shape? What if the sign had a very irregular geometry? Where do we place that vector? That's going to be a topic of discussion in exam 3 land. Okay, now, The remaining unknown is the reaction at A, okay? Now, this is a three-dimensional reaction, and I don't know it, okay? Now, whenever you don't know, and this was the case with support reactions in 2D, we need to make an assumption about direction. What I'm going to do is I'm going to assume that all of these components are positive. And what I mean by that is we're going to have an AX, an AY, an AZ. And I'm drawing those along their positive direction along each of these axes. And that's just going to make the math a little simpler later. It's also going to tell me that if I get a negative answer, it's going to be very easy to determine what those values are. But does everybody see how I've drawn that? So that is the positive X, the positive Y, the positive Z. Everybody okay with that? So let's look at our force vectors. Okay, so we have 4 of them. Okay, let me move this down a little bit because I'm going to refer to that later. We have 4 of them. So the first one, which I'll call the A vector, is just going to be this. Okay. I have what I'll call a W vector, which is like that, and that's in pounds. But then I've got 2 remaining vectors. I've got TBD and TEC. And what I'm going to do is I'm going to say those are some unknown magnitude times a unit vector. Some unknown magnitude times a unit vector. So before we move on right now, I'm going to take a second and I'm going to determine what these unit vectors are. By now, we should be pretty good at that, okay? So let's see if we can do that over here off to the side. So we need a BD, and we need an EC. So given the number of calculations we're going to need to do for this problem, let's see if we can eyeball this a little bit. So for BD, we're going along the x-axis. We're going -8. Along the y, we're going +4. And along the z-axis, -8. Does everybody kind of see what I'm talking about here? So from B to D, along the x, we go -8. Along the y, we go +4. And along the z, we go -8. Is that okay? And for EC, similar determination. Well, if I'm doing that too fast or you want me to go through that, let me know. Okay? Is that okay? So again, -6 on the x, 3 on the y, +2 on the z. +2 on the z because for this way we're going positive along the positive z-axis. Sound good? So now what we need to do is we need to take these, convert them to unit vectors. So here I'll move these down a little bit. And so we need magnitudes for each of these vectors. Making sure everybody's awake this morning. What's the magnitude of vector BD going to be? 12. Do I have a second on that? Making sure everybody's awake this morning. We're just going to use the Pythagorean theorem. Think you're shaking your head yes? So that's 12 feet. How about EC? We got a magnitude for that one?
7 feet.
7 feet. Do I have a second? All right. So therefore, lambda BD is going to be that divided by 12, that divided by 12, that divided by 12. So 2/3, 1/3, 2/3. So here, I'll dispense with the parentheses just to keep this simple. And so this one's going to be sound good? And so what I can do is I can rewrite these up here as TBD times this. And this one like this. So what I'll do is just to organize this a little bit better. Let's do that down here a little bit. Okay. While everybody's catching up, let's just sort of take stock of what we just did. What we have done is we have defined all of the forces on this system in IJK notation. And what we have identified specifically is the number of unknowns that we need to deal with. And I propose that the number of unknowns we need to deal with are 1, 2, 3, 4, 5. Those are our unknowns. But we actually have a system that has 5 unknowns. We actually have 6 equations of equilibrium. What you're going to find in some of our 3D equilibrium problems that we're doing in here is that that's kind of on purpose. The problems are set up in a certain way such that the number of unknowns are a little bit more manageable and a little bit more easy to solve. I mean, technically, we could have a system that has 6 equations, 6 unknowns. Just gets a little bit difficult to solve with one of these. So, not conceptually more challenging, just got to break out MATLAB. You all like MATLAB, right? I'm not seeing the resounding excitement about MATLAB. I'm getting the feeling you don't like it very much. Holding back your opinions, I see. This guy right here, he's holding back his opinion. That's okay. That's okay. Is everybody with me so far? Anybody have any questions? Okay. What? Oh, somebody likes MATLAB. That's what it is. Okay. The next thing that we need are position vectors. Okay. Now, let's take a step back. Here's our system. How many unknowns do we have? 5? We have an AX, an AY, an AZ, a tension in this cable, a tension in that cable. So help me out with something. If you were to pick a location about which to sum moments, where do you think we should pick? Well, what did we do in 2D? We said pick the location where we have a lot of unknowns crossing through it. Say it again. 100% right. We are going to sum moments at A. That's where we're going to sum moments. So our weird Dr. Mike eyeball is going to be focused on point A. But what that means in the land of three dimensions is that we need position vectors that measure from A. Okay? So what are the forces in this system that don't go through A? Well, we have, and I'll draw them in red, we have this force, and that force. So what that means is that we need position vectors that go from A to each of these 3 points. So we're going to need a position vector that looks like that. We're going to need another position vector that looks like that. And one that looks like that. So we'll call these R to B from A, R to E from A, and we'll call it R to W from A. Let's start off with the first one. The beauty of this problem is that these are pretty easy to figure out. What is the vector from here to here? If I were to describe that in IJK notation, how would I do that? It's a really simple one. 8i, that's it, right? 8i. So 8i plus 0j plus 0k. And that is in feet. What about R pointing to E from A? If this was 8i, what's this one? Say it again. 6i, there you go. Lastly, what about W? How far are we going to go along the x-axis? Remember, this is in the middle of the sign. 4. How far along the y? Well, not 2.5. Negative 2.5. We're going down. And z is 0. There you go. That's it. There's your position vectors. So the next step now is to take moments. Okay? And this is, I think, where the problem just gets to be a little bit of a sloth. So let's sort of plan this out. We're summing moments at A. So how many cross products are we going to need to take? We have 3 position vectors, so we're going to need to take 3 of them, right? R cross F for this force, R cross F for this force, R cross F for that force. Okay? So let's just write these out. So we'll call it MW is going to equal R cross F. We're going to have M, we'll call it B. And then we're going to have ME. And what I'll say is over here, note, if we wanted to say the moment from the reaction at A, it would be 0 crossed with A, which is 0. So just to make sure that we're being, comprehensive in our determinations. So far, so good? Now, from here on out, it just becomes a lot of plugging and chugging, okay? So, let me stop for a second. Does everybody have all this written down? Do you need a bit? Still see a couple folks writing, so I'll take a second. Enjoy some of my fine coffee. Yes?
Since there's no K value, can you use the 2D formula?
Since there's no K value, can you use the 2D formula? There is on some of the forces. So that's why. I know it kind of sucks. Now, let me say this. Because of the nature of this problem and because of what you are observing, we are going to find that with all of our cross products, one of those terms is always going to be 0, but not with all of them, okay? So that's where, yeah. Now, if both the forces and the position vectors had no K terms, you're right. You're 100% right. That's a great question. I like that. Sound good? All right. So let's do some evaluation of cross products. All right, so one of these I'm going to do by hand. Actually, no. Let's do a couple of them because I kind of want to make a point about some of these. So the first one I'm going to do is this one. And the reason I'm doing this one first is because it's just numbers, okay? Bless you. Now for this one you're right. This one's going to be 2D, right? And so if you want, you could go through that. But I kind of want to evaluate them all just to kind of make sense of everything. All right, so this one going to be 0, this one 0, and this one we're going to have that times that. So 4 times 270 minus 0. So 4 times 270, that's 1080, so negative 1080. So MW is 0I plus 0J minus 1080K, and that is in foot kips. So there's one of them. Oh, you're right, it is foot-pounds. Thank you. We'll add a 0.05 to the mistake counter on that. Yeah, you're right. Okay, now, the next one I want to take some time with. All right? Now, the next one, let's do the moment from B, right? And so I think we had described that one as R BA cross with T BD. Now let's remember, what was TBD? I think it was the magnitude times I think that was the case, right? So let me show you how I'm going to do this. Here's how I'm going to do this. Let me scroll down a little bit. So the first thing I'm going to do is I'm going to write out my R vector. I'm going to write out my coefficients. But don't forget, I need to include that magnitude. That is an easy mistake to make on problems, that you are going through the process of doing the cross product and you forget the fact that that magnitude is still there. But don't forget that. So the way this is going to work is I'm going to have, okay, so watch this. So we're going to do I times that determinant, so 0, 0, 1/3, minus 2/3, minus j, and then that determinant, right? So that's 8, 0, minus 2/3, minus 2/3, plus k times that determinant, right? Which is 8, 0, minus 2/3, 1/3. But then the whole thing still has a TBD on it, so don't forget that. So what happens when we chug that out? We get 0 here. Here we get 8 times that, which is 16/3, negative 16/3, times that, which is 0. And here we get 8/3 and 0. So we're going to get zero. We're going to get minus j times negative 16/3 plus k times 8/3. But don't forget the TBD. So just to summarize, MB is 0I plus 16/3 j plus 8/3 k, all times TBD. Is everybody okay with that? Let me stop for a second and see if anybody has any questions. Do you need me to hang out here for a sec for y'all to catch up? Okay. See how we're doing on time. Oh, we're doing great. All right. So finally, MC is, ME, not MC, is R E cross A, or E, 2E from A cross with TEC, which is the following. So we're going to have, let's see, I 6 minus 6/7, J 0 3/7, and then K 0 2/7. But then don't forget TEC. Now, if it's okay, if you understand this step, this is exactly the same thing. And in the interest of not wasting time in class, what I'm going to do is I'm going to say that ME ends up being the following. When you chug it out, you get 0I minus 12/7 J plus 18/7 K, all times TEC. If you'd like me to go through that, I'm happy to. For the I component, knock out the rows and columns and you get 0. For the J component, you get 12/7 minus that, but it's negative. And then for the K component, 18/7 minus 0. So. All right. I know, it's a lot of the same thing over and over again. But we're getting there. Okay, with me so far? Okay, so the next thing to do is to now apply static equilibrium. Now, if you remember when we handled the simply supported beam in class, the one that I had to do on the blackboard, remember how we handled our equations of equilibrium in order, but we found we needed to deal with the moment equation first and then substitute back into the force equation. Y'all remember that? If there's any lesson that I want you to take away from dealing with rigid body equilibrium in 3D, it is usually advantageous to sum moments first, okay? Makes the problem a little easier. So we're going to sum moments first. Okay? So what do I mean by that? Well, we have three vectors. Let's write these out. Notice how all of them have a 0I. Okay? All right. Now what about the J component? This one has that. This one has that, and this one has 0J. Let me write these J's off to the side a little bit. What about K? All right, this one has that. This one has that, and this one has that. So notice how I'm writing them in a tabular fashion, and the reason for that is I can now start summing the columns. So this column of values right here is for the sum of moments about the x-axis. But that equation is already satisfied because the sum of these values is 0. So now we have this column and this column to consider. So this is summing moments in the about the y-axis, and this is summing moments about the z-axis. What am I left with? And we'll move the 1080 over to the other side. Break out Casio FX115ES Plus or similar scientific calculator. And you should get the following. That's what you should get when you solve this out. So what that means should mean that. Y'all remember that? 2 equations, 2 unknowns? Or whatever solution strategy you want to use, whatever calculator you have. I want to stop for a second, see if this makes sense. I don't want to just start running through stuff. I want this to be comprehended. Okay?
I'm just stretching.
You're just stretching. Equilibrium. On. I had to. Okay. With me so far? All right. So now, think about this conceptually. We have determined the magnitude of these forces to ensure that moment equilibrium is attained. But what about force equilibrium? We need to sum forces as well, right? How many forces do we have on this problem? I mean, let's go back to the very, 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 very beginning. Well, we have a series of unknowns, yeah, but the number of vectors is 4. Now, the number of forces, yeah, we got 1, 2, 3, 4, 5, and then that force right there. But we have 4 force vectors that those unknowns are collected in. Does that make sense? So what I'm going to do is now I'm going to sum these vectors up. Before I do that, though, I know what these 2 values are, right? So now let's substitute those in, and let's see what we get. And I put the little arrow, yeah. I need to put the little arrow up there. So let's start off with TBD, because remember that's the magnitude times the unit vector, which we now know that magnitude. Here's the unit vector. How are we doing on time? Yeah, we're doing good. Here's that one. We can do the same thing for this one. All right, and what do we get? But then we have two more vectors. We have W. I'll put that over here because that's already in numerical form. And then we have A. And remember, A is that. And the reason I've written it in this way is now I can sum up these columns, sum up these columns, sum up these columns. So this is sum of forces in the x direction, sum of the forces in the y, sum of the forces in the z. And so you just check it out. So summing forces in the x direction equals 0. So, let's see, sorry. So what do we got? We've got negative 67.5 minus 270 plus 0 plus AX has to equal 0. So therefore, just bring everything over to the other side, and AX is 337.5. Same thing with the others. So AY ends up being positive as well. Same thing with summing forces in the Z. Sum them up. I know we're getting close to being done, so I'm trying to hurry. Now AZ ends up being negative, but that's okay. It just means our assumed direction was incorrect. There's the reaction at A. There's our two unknown tensions. Done. I know that's a long problem. Yes. Why is what negative? Oh, so, okay, so check this out. So negative 67.5 plus 90, that's positive 22.5, but it's 22.5 plus AC is 0. So you got to move that over to the other side. That's a fine question. Anybody else? All right, I'm going to pull up the QR code real quick for anybody who came in late, and then I'll pull the notebook back up for anybody who's still jotting down. That's all I got. I'll see you all on Monday.
Pass it all.